New collaboration between the two universities, University of Indonesia and Cranfield University, and also to open pathway for everyone to join the team, to join the global effort to fight the climate change. As Dr. Sila mentioned, this is a global challenges. All right, so this is not just an issue that you have, that we have at in the UK. So this is basically issue for that everyone has. I am sharing my screen. I hope you can see. Can you all see my screen? Maybe thumbs up and let's say, yeah, all right, excellent, thank you. All right, so you have heard about the challenges that Dr. Sila mentioned about the 1.5 degree C or 2 degree C threshold that we have to achieve by 2030 in the UK, or 2050 in Indonesia. And I will start from there, and then I will pick up to what Dr. Sila mentioned about the many colors of hydrogen. So you have heard that there are so many different types of hydrogen, how we produce hydrogen, from the green hydrogen, pink hydrogen, gray, blue, black, and so on and so on. So I just want to highlight the importance of the green hydrogen. The green hydrogen is arguably the most important pathway to generate hydrogen. Reason being is that the green hydrogen, we get all the electricity, the energy required from renewable. And we couple that renewable energy with water, any kind of water, ideally. But right now we use a purified water. And then we couple that to generate hydrogen. So basically it's water splitting, water into hydrogen and oxygen. And then we take the hydrogen as the energy carrier, and then the oxygen will be released to the environment, which is good. So we breathe oxygen, right? So the pathway to decarbonize sectors requires green hydrogen, requires us to use the electrolysis, because then the hydrogen can be used as a synthetic fuel. So if you say you have a CO2, you scrub the CO2 from the environment, you mix it with hydrogen, you can get synthetic methane or synthetic ammonia if you mix that with nitrogen from the air. And ammonia is basically the infrastructure for transportation of ammonia is there. We use that all the time for fertilizer. And then if we stick with the hydrogen as, let's say, as gas or liquefied hydrogen, then we have to ship, we have to transport them in terms of shipping pipeline, or we have to store them somewhere so that it can be used in industry. Now, this is the key bit, is because some of these industry sectors are hard to abate. So this is very difficult to decarbonize. The steel industry, chemical industry, refineries, they are very difficult to decarbonize. Also transportation, particularly the heavy transport. Cars, small cars, that's easy to decarbonize. But HGV, so heavy vehicles, buses, aviation, that's particularly difficult to decarbonize. Hence, we need hydrogen. And if you look at the details, the biggest challenge with hydrogen is on the materials. So everywhere you look at, you will see a materials challenge, from the production, from the transformation, transportation, or end use. everywhere we go, we have materials challenge. I will talk more about the very end point, so the beginning and the end. I only have half an hour or so to talk. Right, so I will focus more on the electrolysis and power generation. So electrolysis is basically, I mentioned earlier about splitting of water into hydrogen and oxygen. Power generation is basically recombining this hydrogen and oxygen into electricity using fuel cell. But that doesn't mean we don't have material challenge everywhere else. We do have challenges in methane synthesis, methane production or green ammonia production. In storage, we have materials challenge because then hydrogen is one of the smallest, lightest molecule. So it will seep out from the storage. So what we call permeation. It embrittle materials, it embrittle steel. If you have steel with hydrogen, the hydrogen will go into the steel and the steel will become very brittle. But I will not talk about that because I don't have enough time to talk everything. I'll just focus on the electrolysis and the fuel cell. The reason why I want to focus on that is because of what I call decarbonization of hydrogen economy. Dr. Sila already mentioned about so many projects are envisioned or are ongoing to be produced or to be started in Indonesia for generation of hydrogen. But I see it slightly differently from the different perspective. Those projects are large-scale projects, but the good thing with hydrogen is that the efficiency of hydrogen production, if you use electrolysis, water splitting, the efficiency is the same whether you go upscale or downscale, whether you start with a very small benchtop electrolyzer or very large scale gigawatt hour electrolysis. In fact, the good thing is that you can couple it with any kind of power generation. Just an example here, I don't think this exists, but in my mind, let's say you go to Tirata, there's a floating solar PV, right? So you can tap the electricity directly from the PV. Underneath the PV, you have the water, plenty of water, and then you couple them together, you generate hydrogen, and then the hydrogen can be used as a cooking fuel, as a agriculture fuel, or you generate electricity directly, which can then benefit directly the community surrounding it. And so you don't have to generate and transport the electricity thousands, hundreds or thousands of kilometers away. The local community can directly benefit. Now, all of this can make sense if we address the main issue with electrolysis. The main issue is practically the cost of the materials. Priscilla already mentioned about everything is so expensive with hydrogen at the moment. Yes. So 95% of hydrogen produced in the world coming from blue hydrogen. So this is basically a methane reforming or CO2 gasification that coupled with carbon capture to produce hydrogen. So the hydrogen right now has a cost about, or at least the target for hydrogen cost is between 1.5 and 2.5 US dollar per kilogram. If you use green hydrogen, so hydrogen produced by electrolyzer, it costs about 4.5 to 6.5 US dollar per kilogram. The reason for that is because of the very expensive cost of electrolyzer. And the electricity price, if we say it's a fixed price of 20 US dollar per megawatt hour, then all depends about on the cost of the electrolyzer. And if we break down the cost of electrolyzer, we can see that the 34% of the total cost of hydrogen production is coming from the materials, the catalyst, the porous transport layer, and then the membrane electrode assembly. So those are on the right-hand side that I highlighted. CCM, catalyst coated membrane, PTL, that's a porous transport layer, MEA, that's a membrane electrode assembly. So just these three components basically accounts for 83% of the capex, capital expenditure of the electrolyzer. So this is a key, because if we can drive down the cost of these three components, we are good. We can reduce the capex, the capital expenditure. We can reduce the hydrogen production cost. If the cost is low, everyone's happy. Everyone can use the hydrogen. Right. So I'll mention about the electrolyzer and fuel cell. For me, they are the same thing. The only difference is that what is the input and what is the output? What do you put in and what do you get? Right. So, in fact, in my lab we have a cell that can be used for electrolyzer or fuel cell depending on what is the input and the output. On the left hand side, this is electrolyzer. Basically, you have an anode, cathode, and electrolyte in between. The input is water and electricity. When you power this, you then generate oxygen and hydrogen. So it's basically splitting water. Now, if you reverse the polarity or the input and output, let's say you put in oxygen and hydrogen, what you get is water. You recombine the hydrogen and oxygen into water and electricity. So for you who are interested more on the chemistry side, so you can see that this is basically the same thing. Like you have a cathode for electrolyzer, you generate hydrogen. On the anode, you generate oxygen. And then if you reverse, you have a reduction of oxygen into O2 minus, or you have oxidation of hydrogen into proton, H plus, on the cathode and anode respectively for fuel cell. And so those are the same thing. So hence for this talk, I interchangeably say about electrolyzer or fuel cell. So if I say this is for fuel cell, that also applies for electrolyzer. If this is for electrolyzer, this also applies to fuel cell, because in reality they are the same thing. It's just the only difference is just the input and the output, what you put in and what you get. Now, how does it look like? This is a benchtop electrolyzer. Basically, on the center there, this is a fuel cell or electrolyzer that has been opened. So you have an end plate, you have an electrode, and then you have a bipolar plate with a flow field. The flow field is basically to distribute the water. So you can see there's a serpentine-like structure, or this interdigitated flow field. So basically, it to just distribute the water, and then this will be in contact with microporous layer. And then microporous layer or gas diffusion layer is basically like a foam where you distribute all the gases or all the water. And sandwiching in between is the MEA, membrane electrode assembly. Now, whether this is a benchtop or a very large scale, so they are basically practically the same. So the difference is that you can stack this, just like battery, you can stack multiple cells to get a higher potential, higher voltage, of higher current, for instance. So when you have all of these components, then you sandwich all of this together. So you can see that this is a schematic of this. So the bipolar plate and the end plate basically on the outer side, and then inside there is a GDL, the gas diffusion layer, and the microporous layer. In between, you have this MEA. So when all of these are stacked together, you can see the electrolyzer on the left hand side. That's it. Gas will be coming in from the left or on the right. So for fuel cell, hydrogen on the left and oxygen on the right. And then it will be split by the catalyst and then exit as water. So let's take a look. What are the components? So basically how it works is basically just electron and ion transport. But everything about fuel cell or electrolyzer is electron and ion transport. Let's take an example here is a fuel cell. Right, so if you have hydrogen on the left hand side as the inlet, and then oxygen on the right hand side as the inlet, another inlet. Hydrogen will travel from one of the inlet through the gas diffusion layer, through the microporous layer, and reach the catalyst of the anode. Upon reaching the catalyst, the hydrogen will be split into proton, right? And then the proton will be transported through the membrane, and then this proton will recombine with oxygen that's traveling on the other inlet, and recombine with oxygen. The proton will recombine with oxygen on the catalyst at the cathode side, and upon recombination, it will accept the electron from the external load. So the electron is coming from on the other side. So the electrons basically release when we split the hydrogen on the anode. And then the act of recombining proton with oxygen with electron result in water, and then the water will be expelled. So what are these materials? Basically, for microporous layer, so this is the interface between gas diffusion layer and the catalyst. These are basically fluorinated polymer. So it can be hydrophobic for fuel cell or hydrophilic for electrolyzer. The reason we want hydrophobic fluorinated polymer is that we want to repel the hydrogen, the water. Water is the byproduct or the product of fuel cell. So we want it to be expelled as quickly as possible. We don't want that to create bottleneck. On the other hand, for electrolyzer, the fluorinated polymer has to be hydrophilic because you want to attract water. Water will be split by the catalyst, right? So you want it to be hydrophilic. For the gas diffusion layer basically interface the backing plate and the current collector with the microporous layer. So these are basically titanium fiber felt. You can look at the microscope image at the center, bottom center. And these fiber felts are coated with platinum. This is the reason why it's so expensive. Every single fiber of this has to be coated with platinum. First of all, titanium is expensive. It's abundant, but it's expensive because it's so difficult to manufacture. And second is that platinum is very expensive. Why do we need platinum to coat the titanium fiber? That's because platinum is stable in strong acid or alkaline environment, and it is oxidation and corrosion resistant. Without the platinum, the titanium will get oxidized very quickly. Once it oxidizes, it becomes titanium oxide. Titanium oxide is non-conductive, first of all. And worst of all is that it can be corroded. So if you put it in the anode side, the titanium will get corroded very, very quickly. Hence, you need platinum. If you look at the heart of the electrolyzer or fuel cell, you will find the membrane electrode assembly. So this is basically a membrane that is sandwiched by two types of catalysts, the anode and the cathode catalyst. This is very thin. The membrane itself has a thickness of about 50 micron, and the catalyst has a thickness of about 15 micron each. But without this MEA, basically there is no fuel cell, there is no electrolyzer. So this is the heart of electrolyzer or fuel cell. This is where you have the transport of H plus or the proton for proton exchange membrane electrolyzer or fuel cell, or the OH minus if you use the alkaline. Right. So this is very thin, but this is actually very, very expensive. Because let's say the membrane itself, the membrane is made of a perfluorinated sulfonic acid polymer. You perhaps have heard this by its commercial name, so Nafion or Aquifion. So this is fluorinated polymer with sulfonic acid group, terminal group at the end. The requirement is that this has to be ionically conductive, but electronically non-conductive. So you cannot transport electron. It has to be blocking to electron, but it has to be conductive to ion. The challenge here is that the ionomer of PFSA is highly corrosive, highly toxic. right? So the process, the manufacturing process is so difficult, such that the only a few companies, I think a handful of companies, 3-4 companies worldwide that are able to manufacture this. Hence, the cost is very high. And to make it worse, this is non-biodegradable. This is bioaccumulative, right? So PFSA is a challenging material, but without this, we don't have green hydrogen. So this is still a challenge to be overcome. Now, to make it worse is that in terms of the cost, right? We have catalyst. Now, catalyst is also extremely expensive because it's currently made of expensive materials. If you look at the catalyst layer, you will see this kind of structure. So these are nanostructures. You have carbon, and with dotted bright dots here, those are the catalysts. So if I zoom in, if you look at this, so this is basically just most of the material here in the catalyst layer are just carbon. Carbon is very cheap. However, this carbon is decorated by platinum. The platinum is the one that's very expensive. So the catalyst itself is the platinum, not the carbon. Carbon is just the structure to hold the platinum catalyst. Carbon is conductive, electronically conductive, hence it's a good structure to hold the platinum. Now, what is the reason for catalyst is, as I mentioned earlier, you need catalyst to break down the hydrogen gas, H2, into the proton on the anode side. And you need to recombine the proton with oxygen gas on the cathode side. Without catalyst, the energy to break down the hydrogen or to recombine oxygen with proton is very high. So the efficiency becomes very low. We're talking about like 20% or lower efficiency without catalyst. And it just makes no sense to generate hydrogen without catalyst. And so the electricity is better used for something else. But with catalyst, especially platinum here, you can easily break down the hydrogen gas or recombine into proton, and then the proton can be recombined with oxygen, so that the efficiency of electrolyzer or fuel cell usually in the order of 80% or above. Right? So this is the importance of catalyst. Now that being said, right, so this is the biggest challenge at the moment. This is a volcano diagram of catalysis. So if you are learning a little bit about chemistry, you perhaps have seen this volcano diagram. So basically in the y-axis, this is the activity, hydrogen evolution reaction activity. And the x-axis, this is the bond strength between the metal and the hydrogen. On the left-hand side, this is the limit of absorption. So basically all the materials on the left-hand side has a weak metal to hydrogen bond. On the right-hand side, you have a strong metal to hydrogen bond. So a good catalyst will sit at the center, basically a balance between a strong absorption and desorption. You don't want it to absorb too strong or to desorb too strong. Right? So you want it to be at the center. So if you look at the center there, all of these materials are platinum, rhenium, rhodium, iridium. These are what we call platinum group metals, very rare and very expensive. Unfortunately, those four materials are the catalysts that we use for proton exchange fuel cell or proton exchange electrolyzer. Well, there's a good thing is that there's an alternative. So you can see it's not as good as those platinum group, but nickel, cobalt, and iron is also an alternative for catalysts. In fact, they have been used for alkaline exchange fuel cell or electrolyzer. They cannot be used in proton exchange because of nickel, cobalt, and iron dissolved in low acid, in low pH, in acidic environment. So hence they can be used in alkaline environment. However, they are not, the catalysts are not as efficient, as effective as those of platinum group metals. And to make it worse, like let's say we go with nickel or cobalt or iron, is that this is what we call materials consumption. The catalyst get deactivated or dissolved over time when we use the catalyst for electrolyzer or fuel cell. Just an example, on the y-axis there, this is the amount of materials that get consumed in kilogram per gigawatt hour output for electrolysis. And the x-axis, these are different types of materials. Just to give an example, 1 gigawatt hour is the energy that required for an airplane to transport 250 passengers, so mid-size airplane from London to Jakarta. Right. So if we use nickel as a catalyst, we will consume 10 kilogram of nickel just for one flight medium-sized airplane from London to Jakarta. Although nickel is very cheap, 1.5 kilo, 1,500 pound per kilogram, right? But in accumulation, if we consume 10 kilogram of that, you can see it costs 15,000 pound per flight just from the material consumption. In contrast, if we use platinum, the consumption of platinum is only in the order of gram or even milligram. Even though platinum is very expensive, this is 450,000 pound per kilogram, but because we only consume a milligram of that, for the same energy requirement, platinum is actually still cheaper than the use of nickel. However, if you look at platinum, this is the biggest challenge. So in terms of cost, yes, platinum is expensive, but if you use nickel, nickel is more expensive because of the consumption of the material. The biggest challenge with using platinum or iridium, rhenium, rhodium is not about the cost, but it's about the availability, the abundance of these materials. So if we look at this table, this graph here, this is abundance on the y-axis, z-axis, that's the atomic number of the materials. Those materials that required for a catalyst for the proton exchange, fuel cell or electrolyzer, are one of the rarest elements. There's just not enough platinum or iridium for everyone. If everyone goes with green hydrogen, if we need every country, everyone, every people on Earth wants to generate hydrogen with electrolysis or use the hydrogen in fuel cell, there's just not enough platinum or iridium or rhodium or rhenium for everyone. So this will create a conflict material. Nickel, cobalt, or iron, even though they are more expensive, you consume them because of the consumption, right? They are more abundant, so you have plenty of them. So everyone can have access. The good thing about nickel is that, just to highlight, Indonesia is one of the biggest producer of nickel. So there's a big mining of nickel in Indonesia. However, you have to be careful here. Most of the nickel are currently processed and refined in China. So there is still a geopolitical issue. But if you are able to refine and process, when I say you, but everybody in Indonesia, right? So if we can refine and process all the nickel domestically in Indonesia, then imagine you hold the share of catalyst production for hydrogen economy, at least 35–40% of that. So I think that's a win. The last bit I want to talk about is the activities that I have been doing in my lab. So because of these challenges, because of the high cost and the inavailability of platinum group metal and the high consumption of nickel for catalysis. In my lab, we focus on other abundant materials that's free from platinum or iridium for both the catalyst and for the for coatings. So we want to replace the platinum, for example, with niobium carbide, molybdenum carbide that are more abundant and cheaper. We want to replace the iridium with calcium manganese oxide or nickel cobalt oxyhydroxide that are again much more much cheaper and more abundant. Now, the good thing is that because these are oxide, the oxide is stable in oxidizing condition. So the consumption, their consumption will be much less if we just start with nickel metal, right? So then if we oxidize, we create an oxyhydroxide, we predict, we are still, the research is still ongoing, but we predict that the materials consumption will be about at least 2 orders, or if not 3 orders of magnitude lower than if we just start with a nickel metal. And with the same material, we want to coat, we are coating this bipolar plate, the gas diffusion layer, to basically prevent corrosion. Corrosion usually happen if the water is not pure, like 100% pure. You have chlorine, right? So chlorine comes from salt. It's everywhere, especially if you use salt water or you have salt seeping from the soil. So the chlorine will basically attack, or if you have steel, this will corrode the steel very quickly. So this is the reason traditionally we use platinized titanium. Our goal is to replace this platinized titanium by carbide or nitride stainless steel. Stainless steel is cheaper than titanium. And the methodology we use for that is what we call high throughput magnetron sputtering, combinatorial magnetron sputtering. So we can mix different materials in gaseous form, and then we mix and then we test them in a band scale electrolyzer or fuel cell. And I would like to acknowledge the funding from Henry Royce Institute and Innovate UK and our partner Hard Earth Coatings in our endeavor to discover new sustainable and economical materials for the catalyst and also for the corrosion resistant coating. With that, we received earlier this year a gold award for excellence in hydrogen research and innovation, and I hope you will see some of our papers published very soon on this. And with that, I will thank. So if you would like to join our team, again, this is a global effort. Joining our team as collaborators, as students, please feel free to contact me. You can find my email and my phone number there, or visit my website. Thank you. I'll stop here.